Alright, our group's topic was rules of influence with quantifiers. We're group B25, which consists of Anirudh Arora, Zachary Berg, and Rachel Chow. And our goal kind of is to simplify rules of influence, or explain, why these are useful. It's not too clear looking at these, just in the table that's in our textbook, why these should be true, or what use you could have for them. Well, rules of inference are used to draw a logical conclusion in a complex argument that helps you simplify things, that helps you understand a flow of the argument. For example, we have modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, addition, simplification, conjunction, and resolution, and we'll go through most of these using an informal proof with a truth table to kind of help make clear of why these should be true and why they're useful. So let's start off with a very common rule of inference, modus ponens, so it's used quite often. And it says P implies Q, therefore Q. In other words, it says if we know that P is true, we know that P implies Q is true, we can conclude, or therefore Q is also true. Now why can we say that? Well, we look at a truth table here. Now let's go through the rows. We know that P is true, so it's only this row or this row in the truth table. And we know that P implies Q is true. So it's pretty simple to see, by rule of elimination, that the only value Q could ever take is true. And it's pretty clear if you know the truth table for P implies Q why this works. If Q is false, the whole statement would evaluate the false. But we know that P implies Q is true, so that can't happen. And this is the tautology for this statement, modus ponens. P and P implies Q implies Q. Now, tautology is just a statement that's always true, and it doesn't matter the values of P or Q. The statement always evaluates the true as a whole. Now let's move on to kind of the contradiction of modus ponens, modus tollens, which says if not Q is true and P implies Q is true, you can conclude that not P is true. In other words, if you know Q is false, P implies Q is true, P must be false. So let's look at this statement. Not Q, when is that true? It's true here and here. And we know that P implies Q is true. Thus, the only statement that the only value P could ever have is false. It's a pretty easy rule of elimination to see why. And we know this because the only time that P implies Q is true when Q is false is if P also has the false value, which makes sense. This is a very useful tool to simplify arguments, as we'll see later in the examples. Now here we have disjunctive syllogism. This one's pretty simple. We all know the truth table for an OR statement. Truth table for an OR statement says that if P or Q or both are true, this OR statement evaluates the true. It only evaluates the false if both P and Q are false. So let's look at this. This is saying if we know that P or Q is true and not P is true, in other words, Q is false or P is false, we know that Q is true. This is almost an obvious statement. You could also say that if P or Q is true, and you know that not Q is true, P must be true. And let's look at the truth table real quick for a quick reasoning why. We know that P or Q is true. We know that not P is true. In other words, P is false. Therefore, Q must be true. That's the only value you could take to make this statement be true. Moving on. Hypothetical syllogism. This one's a little complicated. Let's read through it. It says P implies Q is true, Q implies R is true, therefore P implies R is true. Now, the only way to do this by looking at the truth table is to kind of look at the rows where P implies Q is true and Q implies R is true, and evaluate that P implies R is also true, which once you lay the whole table out is pretty simple to do. So P implies Q is true here, it's Q implies R is true here, and we can see that P implies R is also true. In every case, here is a case, true, 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 and these last two rows as well show that if we know that P implies Q is true and Q implies R is also true, P implies R is always true. Now it's not so obvious at first glance why that would be true. We're looking at this tautology, which states that P implies Q and Q implies R is true, therefore we know P implies R. It's not obvious at first glance why this is true, but using the truth table as kind of a tool of simplification to understand this really helps to clarify it. Now then, finally, we have resolution, the last rule of influence we'll be explaining before we do some examples, which states P or Q, not P or R, is true. Therefore, we can conclude Q or R is true. Now, this one's a little complicated to use a truth table for. It's a little hard to set up, so we thought it might be easier if we just went through and explained in kind of an even more informal proof why this makes sense. So let's look at the tautology here, which is pretty helpful. It says if P or Q is true and not P or R is true, we know that Q or R is true. So an AND statement evaluates as true if both this statement here and this statement here are true. So we know that both P or Q must be true and not P or R must be true. Now P or not P can only have two values. It can only be false or true, so either P is true and not P is false, or P is false and not P is true. So basically what this is telling us is one of these statements automatically evaluates to true because we know that P is true in one of them. So now we know that the whole thing, this whole AND statement evaluates to true as well. So if one of these statements is true, we know that Q or R must be true because in one of these statements P is false. So for example, if P is true here, then this P is false, and that means R must be true to make this whole thing evaluate. And in reverse, if P is true here and P is false here, we know that at least Q must be true to make this whole AND statement work. So therefore we can conclude P or Q and not P or R implies that Q or R is true. At least one of them. Now it could be the case that Q and R is true, but not always. So it only implies Q or R. And that's resolution.
Our first example gives you just a little taste of the rules of inference. Let P be the proposition, Steve likes math. Let Q be the proposition, Steve does his homework. Let R be the proposition, Steve fails his math test. The hypothesis in this case would be P implies Q, and Q implies not R. To construct this argument, we first start with P, and P implies Q. From this, we get Q from modus ponens of 1 and 2. Using the third part of the hypothesis, Q implies not R, we can conclude, using modus ponens again, not R. Our conclusion is Steve does not fail his math test. Our next example has 4 propositions. Proposition 1 is P and T implies R or S. Proposition 2 is Q implies U and T. Proposition 3 is U implies P, and Proposition 4 is not S. We want to conclude that Q implies R. First off, we get P and T implies R, which is a disjunctive syllogism of P1 and P4. Secondly, we use Q implies U and T to get Q implies U and Q implies T, which is a conjunction of proposition 2. For our third step, we get Q implies P by using resolution of proposition 3 and 2a. Our fourth step is Q implies P and T, which is a conjunction of the third step and 2b. For our fifth step, Q implies R is our conclusion, which is just a resolution of 1 and 4. And that's all there is to it.